Examples of Malus's law in classical physics and quantum mechanics. Bridging classical and quantum worlds. Video number 2 of 2. In quantum physics, light is considered to be made up of photons, which are particles. Here's where the weirdness comes in. 1. Photon behavior. Individual photons behave probabilistically. When a photon encounters a polarizer, there's a probability that it will pass through, based on the angle between its polarization direction and the polarizer's axis. This probability follows Malus's law, but the outcome for each individual photon is inherently random. Polarization is not a fraction of light getting through, but a probability of individual photons passing. 2. Superposition and entanglement. Quantum particles can exist in superpositions, meaning a photon can be in a state that's a combination of multiple polarization directions. When measured, it collapses to a definite state. Also, entangled photons exhibit correlations that can't be explained classically, which further complicates our classical intuition. 3. Wave-particle duality. Light exhibits both wave-like and particle-like properties. Malus's law in quantum mechanics respects this duality, as it has to explain both the probabilistic nature of individual photons and the wave-like interference patterns they create. The weirdness lies in these quantum principles that challenge our classical understanding of the world. While the mathematical results are the same, the quantum interpretation introduces concepts like superposition and entanglement that don't have classical analogues. Let's see how the probabilistic behavior of a photon when encountering a polarizer is indeed linked to superposition. In quantum mechanics, a photon's polarization state can be described as a superposition of basis states. For example, if we consider horizontal and vertical polarization as our basis states, a photon's polarization state can be a combination of these, such as psi ket equals alpha h ket plus beta v ket, where alpha and beta are complex numbers that determine the probability amplitudes for the horizontal and vertical components. The probabilities of measuring these components are given by mod alpha squared or absolute alpha squared and mod beta squared or absolute beta squared, respectively. If the coefficients and beta are real numbers, the expression simplifies to ket psi equals alpha horizontal plus beta vertical, where alpha and are real numbers, not complex. This is the simplest case, where the coefficients are just regular real numbers for the representation of a quantum state, e.g., the polarization of light. When a photon encounters a polarizer set at an angle theta to its initial polarization direction, the probability that the photon passes through the polarizer is determined by projecting the photon's polarization state onto the axis of the polarizer. This projection inherently involves the superposition of the component vectors. Malus's law essentially describes the process of projecting a photon's polarization state onto the axis of a polarizer. How Malus's law relates to projection. A photon with polarization state encounters a polarizer aligned along some axis. The probability of the photon passing through is given by the squared projection of ket onto ket. Mathematically, if the initial polarization is ket psi equals cosine phi horizontal plus sine phi vertical, and the polarizer is at an angle theta, the projection gives P equals the absolute square of the inner product of theta ket and psi ket, which equals cosine squared of theta minus phi. Or, more simply, P equals mod bracket theta psi squared, which equals cosine squared of theta minus phi. P equals the absolute square of the inner product of theta ket and psi ket, which equals cosine squared of theta minus phi, which is exactly Malus's law for probability. The same equation applies to intensity when dealing with classical light waves. Malus's law can be understood in terms of the dot product, or inner product, of vectors in a Hilbert space. A photon's polarization state is a vector in a 2D complex vector space. A polarizer aligned at an angle selects a new basis vector. The probability of the photon passing through the polarizer is given by the squared magnitude of the inner product, dot product in the appropriate space. If the initial polarization state is written in terms of horizontal and vertical components, the state psi equals cosine phi times horizontal ket plus sine phi times vertical ket, and the polarizer is at angle theta, then theta ket equals cosine theta h ket plus sine theta v ket. The inner product, dot product, of these two states is the inner product of theta ket and psi ket equals cosine theta cosine phi plus sine theta sine phi, which equals cosine of theta minus ph. Since probability is given by the squared magnitude of this projection, P equals the absolute square of the inner product of theta ket and psi ket, which equals cosine squared of theta minus phi. Conclusion. Malus's law is based on the dot product of two unit vectors, polarization states, and the probability of transmission is given by the squared cosine of the angle between them. The probabilistic behavior of photons in the context of Malus's law is deeply rooted in the quantum concept of superposition, where the photon's polarization state is a combination of component vectors, and the measurement process projects this state onto the polarizer's axis.